Good morning, children. Today we'll begin chapter 7 of physical chemistry, equilibrium, part 1. In this presentation, we will study about physical and chemical equilibrium. Now, these are the answers of the questions in chapter organic chemistry, part 9. You may verify your answers from here. Now, we begin with physical equilibria. Now, the equilibria involving physical processes are referred to as physical equilibria. And it may be of the following three types. Number 1, solid-liquid equilibria, liquid-vapor equilibria, and solid-vapor equilibria. Now, as far as solid-liquid equilibrium is concerned, for any pure substance, the temperature at which the solid and the liquid phases are at equilibrium at 1 atmospheric pressure is called the normal melting point or normal freezing point of the substance. For example, when a solid is taken at its melting point, both solid and liquid phases exist in equilibrium. As you can imagine, when a solid is heated, it turns to liquid at its melting point, and on cooling, at its freezing point, the liquid changes into solid. So the two phases simultaneously and continuously change into each other. This is why equilibrium is said to be dynamic. So the rate of change of melting is equal to rate of freezing. The equilibrium is dynamic, and the change in free energy, delta G of the system, is equal to 0. For example, ice changing into water and water changing into ice at 273 Kelvin and 1 atmospheric pressure. Number 2 is the liquid-vapor equilibrium. Now, this can be established only when the rate of evaporation becomes equal to the rate of condensation. Then a dynamic equilibrium is attained. For example, when you heat a liquid, it turns to vapor, and vapors on condensation turn to liquid. But this can only happen in a closed system, in a closed container. In an open container, the vapors will disperse in the atmosphere and equilibrium cannot be obtained. Third is the solid-vapor equilibrium. Now, there are several solids which undergo sublimation, that is directly change into vapor on being heated without changing to the liquid state. In such a case, an equilibrium is established between the solid and its vapor. For example, ammonium chloride solid on heating changes into ammonium chloride vapor, and the vapors on cooling will change into ammonium chloride solid. Now we begin with chemical equilibrium. Now, chemical equilibrium is a particular state of a reversible reaction in which the forward and the backward reactions occur at the same rate, and the concentrations of all the reactants and the products, they remain constant, that is, do not change with time. Now, for example, if you see the reaction A plus B, which gives you C plus D, and then C plus D gives you back A and B, it's a reversible reaction. Now, consider this reaction in equilibrium in a closed vessel. When the reactants A and B are mixed together under suitable sets of conditions in a closed container, the forward reaction proceeds to form products C and D. Therefore, with increasing time, the concentration of reactants A and B decreases, while those of the products C and D will increase. At the same time, the backward reaction also takes place, and the products C and D combine together to give back the reactants. Thus, both forward and the backward reactions take place simultaneously. Now, since the concentrations of the reactants decrease and those of the products increase with time, the rate of forward reaction decreases with time, while that of the backward reaction increases with time, as you can see in this graph over here. After a certain time, a stage is reached when the rate of the forward reaction becomes exactly equal to the rate of the backward reaction, as shown in the figure. This state is known as the state of chemical equilibrium. Now, you can see this in the graph by a straight line. So here at chemical equilibrium, we say rate of forward reaction is equal to rate of backward reaction. Now, the characteristics of chemical equilibrium. Number 1, constancy of observable properties. Now, all the observable properties of the system acquire constant values at equilibrium and do not change with time. For example, concentration, color of the equilibrium mixture, specific rotation, etc. They all remain constant. Number 2, attainment of equilibrium from either side. Now, the state of equilibrium can be attained from either side, that is, it makes no difference whether we start from the reactants or from the products. Third, dynamic nature. Now, the forward and the backward reactions do not stop at equilibrium and occur continuously at equal rates, no matter how long the equilibrium is maintained. Therefore, the chemical equilibrium is dynamic in nature. Number 4, Equilibrium cannot be attained in an open vessel, means it can be attained only in a closed vessel. If the vessel is open, some of the products may escape from it and the backward reaction may not take place. Therefore, equilibrium will not be attained. Number 5. Equilibrium point remains unchanged in the presence of a catalyst. Now, the presence of a catalyst does not change the equilibrium point. A catalyst, catalyzes both forward and the backward reactions to the same extent. Therefore, the equilibrium may be attained earlier, but equilibrium point remains unchanged. Now we come to the law of mass action. Now this law was stated by Goldberg and Wage in 1864. It states that at constant temperature, the rate of a chemical reaction is directly proportional to the product of the active masses of the reacting species, with each active mass raised to the power equal to the stoichiometric coefficient of that species in the chemical reaction. For example, let us consider a reaction A plus B, which gives you some products. So according to the law of mass action, rate of reaction is directly proportional to the product of the molar concentrations of A and B. Or we can say rate of reaction is equal to K into A in a square bracket into B in a square bracket. The square bracket represents the molar concentration. Now here K is a constant of proportionality known as rate constant. Now let's take a general reaction where A molecules of A react with B molecules of B and C molecules of C to give some products. So in this reaction, A, B, C represent the numerical coefficients of the species A, B and C respectively and are the stoichiometric coefficients. So applying the law of mass action, we have rate of reaction is proportional to the product of concentration of A raised to the power A into concentration of B raised to the power B into concentration of C raised to the power C. Or rate of reaction is equal to K A raised to the power A into B raised to the power B into C raised to the power C, as you can see in the last equation. Now we come to law of chemical equilibrium and equilibrium constant. Now this law is a mathematical expression and can be obtained by applying law of mass action to a reversible reaction in equilibrium, like A plus B reacting reversibly to give C and D. Now here an equilibrium exists between the reactants A and B and the product C and D. So let A, B, C and D in square brackets represent the active masses, that is the molar concentrations of A, B, C and D respectively at equilibrium. So according to the law of mass action, the rate of forward reaction is directly proportional to the molar concentrations of A into B, or we can write it as equal to K1 A in a square bracket and B in a square bracket. Rate of backward reaction is directly proportional to the active masses, that is molar concentrations of C into D, which can be written as equal to K2 C in a square bracket and D in a square bracket. Now here K1 and K2 are the rate constants for the forward and the backward reactions respectively. Now at equilibrium, the rate of forward reaction is equal to rate of backward reaction. So we can say K1 A into B is equal to K2 C into D, or I can say K1 upon K2 is equal to the active masses of C into D upon A into B. Now at a particular temperature, K1 and K2 are the constants, therefore the ratio K1 upon K2 will be a constant. This is represented by K and is called as the equilibrium constant. Thus we can say K is equal to K1 upon K2 is equal to the molar concentration of C into D upon the molar concentration of A into B. Now for a general reaction of the type where A molecules of A react with B molecules of C reversibly to give you C molecules of C and D molecules of D, the expression for equilibrium constant can be written as K is equal to the molar concentration of C raised to the power C into molar concentration of D raised to the power D upon the molar concentration of A raised to the power A into molar concentration of B raised to the power B. Now these expressions are for the law of chemical equilibrium. These are also known as equilibrium constant expression. So we can define the equilibrium constant as follows. Now equilibrium constant K is the ratio of the product of the active masses, that is molar concentrations of the products, to that of the reactants in equilibrium, with each active mass term raised to a power equal to the stoichiometric coefficient of the substance in the balanced chemical equation. Now the equilibrium constant K is also represented as Kc and Kp depending upon the unit of the active mass and in the expression used in the expression. When active masses are expressed in terms of concentration unit, K is written as Kc, and in case of active masses are expressed in partial pressure unit, then K is written as Kp. Now next is equilibrium constant in terms of partial pressure, Kp. Now when all the reactants and products present in a reversible chemical reaction are in the gaseous state, the equilibrium constant K is written in terms of partial pressure. This is because partial pressure of a gaseous substance is proportional to its molar concentration, as we have discussed earlier. Now when the active masses are expressed in terms of partial pressure, the equilibrium constant K is written as Kp. So let us consider a reaction, a general reaction, where A molecules of A in the gaseous state combined with B molecules of B in the gaseous state. The reaction is reversible to give C molecules of C in the gaseous state and D molecules of D in the gaseous state. So let PA, PB, PC and PD be the equilibrium partial pressures of A, B, C and D respectively. So applying the law of mass action and the law of chemical equilibrium, the equilibrium constant Kp for the above reaction can be written as follows. Kp is equal to P into C raised to the power C into P D raised to the power D upon P A raised to the power A into P B raised to the power B, where P represents the partial pressure. For example, let us take a reaction N2 plus 3H2 in the gaseous state combining to give ammonia in the gaseous state. Kp can be written as Kp is equal to P NH3 raised to the power 2 upon P N2 into P H2 raised to the power 3. Now we come to the exercise. Attempt the following questions given on pages 492 and 501. Well, I hope children you understood the lesson today. Good day. Thank you very much.